These examples come out of section 1.3, one-sided limit. We're asked about the square root of x. First of all, we're asked what's the limit as x approaches 0 from the right of square root of x. Now you can try tiny numbers, tiny positive numbers in this case. You could look at a graph and remember that it looks something like this and say, well, that answer to that limit is 0. As you approach from the right, the square root of 0.0001, 0.000001, etc. is 0, or approaching 0. As you try to approach from the left, it's impossible. You have no graph to the left of 0. In fact, you can't square root any negative number and get a real number answer from it, so you get does not exist, which right away tells you that the two-sided limit does not exist, because the only way that it exists is if the right-handed and left-handed limits give you the same answer. Now, let's show something a little bit different. Show that y equals the absolute value of x. If you remember what that looks like, show that it's continuous at 0, or maybe more specifically, show that the limit as x approaches 0 of the absolute value is equal to 0. Absolute value function is a funny function. If f of x equals the absolute value of x, really what it is one of these piecewise graphs, even though you never defined it that way in Math 10, 20, and 30. Absolute value just says leave x alone if x is greater or equal to 0. Change the sign if x is less than 0. If I draw the picture of that, y equals x is a graph that looks like this, y equals negative x is a graph that looks like this, and they do actually connect. If I say what's the limit as x approaches 0 from the left of f of x, it's saying, well, what is negative x approaching as x gets close to 0? And the answer is 0, which equals the same answer if I approach from the right, which tells me that the two-sided limit exists and is equal to 0. So kind of a strange example, and you won't get a lot of show that examples on my test, but it is worth talking about it in the teaching part of the course.